Welcome back, everybody. We are looking at the antiderivative table about the middle of page 102 in the workbook here. And what we're going to try to do is to use the work that we did in example 2 near the top of this page to help us come up with a nice table of antiderivatives for common functions. Okay, and I'd like to start with the function x to the n. See if we can come up with a formula for an antiderivative for that function. It comes up quite a bit when we're taking antiderivatives. Okay, and we can get some insight into that by looking back at some of the problems that we did in example 2 in particular. I'm thinking that D, E, and F up here at the top of the page might help us to answer this question. Okay, so let's start by taking the answers that we got and just simplifying them a little bit. So starting with D here, we got an antiderivative of 1/3 x cubed. Notice that we can rewrite that as x cubed over 3. And our answers for E and F, we can do kind of the same thing, just consolidate them into single fractions. That's going to maybe help us find a pattern a little bit more easily here. Okay, and so if we look at just D for a minute, how did we get from our function x squared to our antiderivative x cubed over 3? Notice that really two things happened. We took the power of 2 that we started with, we added 1 to it, that's where this x cubed came from, and we divided by that new power. So we got x cubed over 3, raise the power by 1 and divide by the new power. Notice that that pattern occurs in E and F as well. Over here at E, we started with x cubed. We raised that 3 by 1 and got an x to the 4th and divided by that 4. Okay, so the pattern we're noticing here is if we start with x to the n, jumping down to the table here, we should be able to get an antiderivative by raising the power by 1, x to the n plus 1, and dividing by that new power. Turns out that that will be an antiderivative for x to the n. And this has a special name. It's called the power rule for antiderivatives. Okay, now that's the first and probably the most important formula on our list here, and I wonder if you notice a possible issue with this formula, x to the n plus 1 over n plus 1. If you think about it, we're going to run into problems if n is equal to -1 because it's going to make our denominator equal to 0, so it's important to note that this power rule only works if n is not equal to -1. So if the power on the x that we started with here, if this n is equal to -1, we've got a problem. We can't use this formula to find an antiderivative. Okay, so if you look at the second row of the table here, they're asking us, is there maybe another antiderivative for the case when the power is -1? Okay, we know that the formula up here is not going to work, but is there another function whose derivative would give us x to the -1? Think back to what we've talked about earlier in the course for a minute. And a hint that I'll give you is x to the -1 could be rewritten as 1 over x. Can you think of a function whose derivative is 1 over x? Natural log works. Okay, so the natural log of x would be an antiderivative for x to the -1. We're going to tweak it a little bit. And instead, we're going to take the natural log of the absolute value of x. Turns out that that's also an antiderivative of x to the -1. And if you're wondering where that absolute value came from, hold that thought. We'll say a word about that once we've filled out the rest of the table. Okay, so moving down our list here, if we start with cosine of x, can you think of an antiderivative of cosine of x? You might look back at example 2 and notice that we figured out that an antiderivative for that is sine of x. What about sine of x? Can you think of a function who's an antiderivative for sine of x? Okay, well, I claim that negative cosine of x will work. Let's check that. Okay, remember, we can check any of our answers here by taking the derivative of the function that we think is an antiderivative and confirming that that gets us back to where we started. And we pull out the minus sign, the derivative of cosine is negative sine, and sure enough, that gets us back to where we started, so we've confirmed that negative cosine of x is an antiderivative of sine of x. Okay, what about e to the x? Okay, well there, antiderivative of e to the x has to be itself because we know that the derivative of e to the x is e to the x. Okay, what if we want an antiderivative of a constant? Okay, can you think of a function whose derivative would give us just the number k? If you think about it a little bit, kx will work because what happens if you take the derivative of k times x, where k is a constant? Well, the derivative of x is 1, and so the k just comes out and we get k, confirming that kx really is an antiderivative. Okay, and the last two, these are a little bit crazy. So could we come up with an antiderivative for 1 over 1 plus x squared? That's a complicated function. Okay, here what we have to do is to kind of think back to something that we talked about earlier in the course. So can you think of a function whose derivative gives you 1 over 1 plus x squared? You might have to look back a few pages to the sections that we did on derivatives, and you'll discover that arctangent of x works because we had a formula for the derivative of arctangent of x that looked like 1 over 1 plus x squared. Okay, and similarly, 1 over the square root of 1 minus x squared, you might recognize that as the derivative of arcsine of x. And so arcsine of x has to be an antiderivative for that function. Okay, and I want to make a comment that some of these formulas are more common and useful than others, so I'm going to put a star by the ones that I think are probably the most important. Okay, well actually, I guess I would put a star by probably the first 6 of these. The last two come up occasionally, but maybe not as often. Okay, now if you're short on time, you can maybe stop the video here and not watch the end of it, but I'm going to say a word about this second formula, where that absolute value of x came from. So if you're interested in why that's there, that's what we're going to talk about now. So if we maybe just number this formula so it's clear what we're talking about here. This is formula number 2. We're going to give just a little brief proof of that. Okay, why is it that ln of absolute value of x is an antiderivative of x to the negative 1? Well, we could start by taking the ln of absolute value of x and noticing that it kind of breaks into 2 cases. So what does the absolute value do to a number? Well, it just makes it positive. So if x is greater than 0, the absolute value of x is just going to be x, so we could rewrite our function as just ln of x. If, on the other hand, x is less than 0, then to get the absolute value of x, we would need to negate the negative number and write it as ln of negative x, the logic being that if we start with a negative number, then negative x is positive. Okay, so we can rewrite our function ln of absolute value of x by breaking it into 2 cases. And what that allows us to do is to take the derivative of ln of absolute value of x kind of in 2 pieces. Okay, so if x is greater than 0, we're just taking the derivative of ln of x, which we know is 1 over x. Okay, but what happens in the second case? If we take the derivative of ln of negative x by the chain rule, we're going to get 1 over negative x times the derivative of negative x, which is negative 1. And what happens if you simplify this? Well, the minus signs cancel, and you get 1 over x. So that part that we circled here is also equal to 1 over x. So what we've confirmed is that the derivative of ln of absolute value of x gives us 1 over x in both cases, and that confirms this formula that we have up here. Okay, so this equals 1 over x for every x that's not equal to 0. Okay, and there's our little proof that formula 2 is correct as we've written it.